Hi all, today we are going to handle the topic dynamics of electrical drives. Numerical problems based on this topic are usually asked in the university question papers. We will begin with the fundamental torque equation. In order to obtain the relation for this fundamental torque, we will consider a motor load system as shown in the diagram here. The torque which is developed in the motor is represented as capital T, and the load torque is usually indicated as capital T suffix small l. Here we have considered a rotational system. It's not necessary that the load must be always having the rotational motion. In certain cases the load might be of having translational motion. In such cases we will be using a rotational to translational transmission system. So these loads may be either having rotational motion or translational motion. While considering the case of rotational motion also, it's not necessary that the load must rotate at the same speed as that of the motor. You have seen in the case of individual electric drives and group electric drives in our previous video session, there are different components of the load were not rotating at the same speed as that of the single actuating motor. But now in this case, for obtaining the relation for fundamental torque equation, we will be considering this particular motor load system. Moment of inertia of this motor load system with respect to this motor shaft is indicated as capital J. The angular velocity of this motor shaft is also represented as omega m. As I mentioned before, the torque which is developed in the motor is indicated as capital T, and the load torque is indicated as capital T suffix small l. Now all of you might have a common doubt why the direction of load torque is indicated as opposite to that of the motor torque here. This is mainly due to the components of the load torque. The main components of this load torque are friction component, windage component, and the torque required to do the useful work. The sense of direction of all these components are in such a way so as to oppose the torque which is developed by the motor. That is the reason why this load torque are indicated in opposite direction to that of this motor torque or the developed torque. From this motor load system, we can obtain the standard relation of fundamental torque equation, that is T minus TL is equal to d by dt of j omega m. That is indicated here. T minus TL is equal to d by dt of j omega m. By using the basic rule of differentiation, that is d by dt of uv, we usually write it as u into dv by dt plus v into du by dt. In the same manner we can write it here also, and we will mark this as equation number 1. This equation is valid only in the case when the value of j is a variable 1. If you are considering this j as a constant one, then definitely this term becomes 0. So I can very well say that this relation is valid only in the case of a variable inertia drives. Some examples of variable inertia drives are mine winders and industrial robots. You don't need to know about them in detail, but you must keep in mind that this relation 1 is valid only in the case of variable inertia drives, because only in the case of this variable inertia drives this value of j will be a variable 1. In all other cases the value of j will be a constant 1, and this term won't exist there. So considering the case of constant inertia drive, so in that case the value of this particular term becomes 0, and then equation 1 gets modified into this form, which is indicated as equation 2, that is T is equal to TL plus J d omega m by dt. For further analysis we will be using this relation. That is, it is very clear that the system which we are going to consider is a constant inertia drive. As we have mentioned before, in this relation this T is indicating the motor developed torque, T suffix small l is representing the load torque, and this J d omega m by dt is indicating the dynamic torque. This is actually a transient component. Transient component means this particular term will exist only during the transient condition. The transient conditions in a drives are actually the accelerated condition or deceleration condition. Now if we are considering this particular term as a 0, 1, that is possible only when the velocity is a constant 1. So when this particular term is 0 means T is equal to TL, and the drive will be always rotating at a constant speed. But in this condition, an additional term is also there, which is actually a transient component 1. So it's very clear that this term will exist only during the transient conditions, and it is said to be the dynamic torque component. Under uniform motion condition, this particular term won't exist there. Not only under uniform motion condition, I can also say it as under steady state condition, this particular term won't exist there. Steady state means the electric drive will be running at a constant speed, or it will be having a uniform motion condition. So this relation can also be written as capital T minus capital T suffix small l is equal to j into d omega m by dt. There are actually two conditions for transient operations. One is accelerated motion and the second one is deceleration motion. In acceleration motion, first we will see the case of acceleration motion. So in acceleration motion, the value of capital T, that is the torque which is developed by the motor, will be greater than that of the load torque. So in that case, T minus TL is equal to j into d omega m by dt value will be positive 1, since the value of T is greater than TL. During this accelerated transient condition, energy associated with this dynamic torque component, that is j into d omega m by dt, will be stored as kinetic energy in the motor shaft, and the relation for that kinetic energy is half j omega m square. Similarly, in the case of deceleration transient condition, the value of TL will be greater than that of T. So this relation T minus TL is equal to j into d omega m by dt becomes negative. That is, in this particular case, the energy associated with this dynamic torque is negative, which means that this dynamic torque will be assisting the motor torque and maintains the drive motion by extracting the kinetic energy stored in the motor shaft. So we have clearly explained the two transient conditions. One is during the acceleration transient condition and the second one is deceleration transient condition. During acceleration transient condition, the value of T is very much greater than TL, and during deceleration transient condition, the value of TL is greater than T. In the case of accelerated motion, energy associated with this dynamic torque is stored as kinetic energy in the shaft, whereas in the case of deceleration condition, the energy associated with this dynamic torque is negative in sign. That means the energy will be extracted from the motor shaft, that is, the kinetic energy will be taken away from the motor shaft. So far we have explained about the fundamental torque equation. The theory portion of our discussion are also written here. Next we are going to study about the components of load torque. In the previous slide we have indicated the load torque as capital T suffix small l, and I have mentioned also there are various components for this load torque. They are friction torque, windage torque, and the torque required to do the useful mechanical work. It is a common scene that the students get confused between this capital T suffix capital L and capital T suffix small l. This capital T suffix small l is actually indicating the total load torque, which is the sum of this friction torque, windage torque, and capital T suffix capital L. Nature of this torque is depending upon the particular application. We will discuss about them in detail in the upcoming slides. Regarding friction torque, you are very well aware about this. Friction exists in all mechanical parts of a system. So in this case, friction will be present at the motor shaft and also at various parts of this mechanical load. This is usually indicated as capital T suffix capital F. Next is windage torque. Whenever this motor is running, wind will be generated surrounding the motor, and the nature of this wind will be opposing the torque which is produced by this motor. So that is usually indicated as capital T suffix capital. Next we are going to see the various components of load torques in detail. We will start with friction torque. This characteristic is indicating the variation of friction torque with speed. This friction torque can be resolved into three components. They are stiction friction, viscous friction, and Coulomb friction. You have studied them in detail during your 11th and 12th standard. While observing the characteristics of stiction friction here, you will be able to see that the value of the stiction friction is maximum under standstill condition, that is when the value of speed is 0. When the drive is gaining more speed, this stiction friction torque keeps on reducing, and at this particular speed the stiction friction almost vanishes. Thereafter we will be left with two components. They are viscous friction and Coulomb friction. From the characteristics of viscous friction, it's very clear that this viscous friction torque is actually directly proportional to the speed. From this characteristics of column friction, it's very clear that this column friction is not having any dependency on the speed term. While combining all these characteristics, we will be able to obtain the final characteristics of friction, torque and speed. Next component of this load torque was the windage torque. The description for windage torque was given in the previous slide. Actually, this windage torque is directly proportional to the speed square. Therefore, the relation for windage torque can be written as TW is equal to C omega m square, where the C is actually the proportionality constant. Now, considering a steady state operation of a drive, in such a system, the relation for load torque can be given as T suffix small l is equal to T suffix capital L. This is actually indicating the torque required to do the useful mechanical work. This portion is representing the viscous component of friction. This one is column component of friction, and this is actually the windage torque. We haven't represented here the stiction component or the stiction friction. As I said now, we have considered a drive which is running at a finite speed, or which is actually in steady operation or steady state operation, rather than considering the dynamic case during starting or stopping. That is, while considering the steady state operation of a drive, that is, the drive will be running at a constant finite speed. For such a drive, the relation for load torque can be given as T suffix small l is equal to T suffix capital L plus B into omega m plus Tc plus C omega m square. We are going to see the various types of loads. In our last session, we have seen the block diagram of electric drive. The two components over there were electric motor and converter. The selection of this particular motor and a particular converter is achieved to meet the requirements of the load profile. You just cannot choose a motor and a converter in random. The selection is done after studying the load profile. So in order to study the load profile, you must able to know under what category of load does it fall. Therefore, the load is categorized into different types. They are constant torque type load, torque proportional to speed. This is also called as generator type load, fan type load, and constant power type load. In addition to this, two more types are also there. We will see them on our way. In all these characteristics, you must know their load torque versus speed characteristics. Please be very careful with this. We are actually plotting the characteristics between load torque, that is T suffix small l, not capital L, T suffix small l and omega. And for all these types of loads, you must know their characteristics and suitable examples. In this constant torque type load characteristics, we have plotted the load torque T suffix small l along x-axis and omega along y-axis. From this characteristics, it's very clear that it's actually a constant torque type load because the torque remains constant for all the speeds. From this characteristics, is very eminent that the main component of this load torque will be the column friction component. As we have seen in our previous slide, the column friction does not have any dependency on the speed. So the majority part of this load torque component will be mainly the column friction component. That's why it's showing this particular characteristics. Examples for this constant torque type load are screw compressors, feeders and conveyors, because they all will be handling fixed volumes. Another examples are those cranes which are during their hoisting operation, and the conveyors, those conveyors which will be handling constant weights of material. From this characteristics, it's very clear that the windage torque component is neglected. This is done so because all this constant torque type loads will be of low speed operation. So you must remember that this constant torque type load characteristics will be like this, and their examples are those which are handling fixed volumes or constant weight materials. Next is generator type load. From the characteristics itself, it's very clear that the torque will be directly proportional to the speed. This is very much similar to the case of viscous friction characteristics. The best examples for this generator type load are helical positive displacement pumps, eddy current brakes and calendering machines. These calendering machines are commonly used in laundry industries, paper industries, etc. Next is fan type load. In the case of fan type load, the torque will be directly proportional to omega square. So the characteristics will be like this. Some more curve will be there. From this characteristics, it's very clear that in this characteristics, as the torque is directly proportional to omega square, the component which will be dominating on is the windage torque. So this will be applicable only in those particular applications which will be running at very high speed. Such sort of examples are in the case of fans, compressors and aeroplanes. Even we can consider the case of ship propellers and high-speed hoist also into these examples. Next classification is constant power type load. From this characteristics itself, it's very clear that if you consider all the points, for the case of low torque the speed is high, and the case of high torque the speed is small. So at all the points the power almost remains constant. Please make a correction here. Here it won't be coming as T suffix capital L, it will be T suffix small l. As constant power is to be maintained, the characteristics will be having a hyperbolic shape. The best examples for this constant power type load are lathe, boring machines, milling machines, steel mill coiler, etc. All the classifications discussed so far coming under the broad category of different types of loads. In addition to this, we have mentioned there also some other loads are also taken into consideration. They are high speed hoist and traction load. In the case of high speed hoist, as the speed is very high, we will be considering only the viscous friction and windage components of the load torque. So in such a case, the characteristics will be like this. You just need to know the characteristics. And the next case is traction load. So in traction load, in order to accelerate such a heavy mass, the developed torque in the motor must be able to compensate the large stiction component of the friction which is present at the standstill condition. As the mass is gaining speed, this friction component keeps on reducing. Thereafter, the viscous friction component and the windage torque component comes into picture. So due to this heavy stiction component, or due to the large stiction component which is present, the characteristics will be having a shape which is identical to that of the friction speed characteristics which we have discussed in our previous slides. Next classification of this load torque is active load torque and passive load torque. Active load torques are those which retain their sign even after the direction of rotation of the drive is reversed. That is the basic explanation of active load torque. This exists mainly due to the gravitational force or the deformation in the elastic bodies. See, if you are considering the case of a hoist operation, whether the hoist is moving in upward direction or in the downward direction, the direction of gravitation pull will be always in the downward direction. That is, the gravitational pull is a good example for this active torque, because their sense of direction is not getting reversed. Whether the hoist is moving in upward direction or in the downward direction, the gravitational pull will be always acting in the downward direction. Similarly, this active load torque will be existing in the case of compression and releasing of the springs. So considering the case of gravitational pull and this compression and release of the springs, it's very clear that this active load torque will be prominent, or we can say they are very much closely associated with the potential energy. In a more easy manner, it can be set like this. Consider the case of upward motion of the hoist. So when a load is moving upward, it's very clear that the potential energy of the load keeps on increasing. The active torque which comes into picture here is the gravitational pull which is acting in the downward direction. So whenever this active torque is acting in the direction of opposite of the real action that is taking place, that is, in the case of hoist, the load is moving upwards and the gravitation pull is acting downwards. So this gravitation pull is the active torque there, and that active torque is acting downwards when the hoist is moving in the upward direction. So whenever this active torque is acting in the direction opposite to that of the real action, then it's very clear that the potential energy goes on increasing. Similarly, we can say the example of spring. Whenever we are compressing the spring, the potential energy of the spring is increased. During the scenario also, the active torque will be acting in the outward direction. Consider in the opposite manner, that is in the downward motion of the hoist. When a load is moved downwards, the potential energy goes on decreasing. Now the gravitational pull, that is the active torque, will be acting in the same direction as that of the real action, that is the load is moving in the downward direction. So when this active torque acts in the same direction as that of the real action, then the potential energy goes on decreasing, whereas when this active torque acts in the opposite direction as that of the real action, the potential energy goes on increasing. Hope it's very clear for you. Next we will discuss about passive load torque. In the case of passive load torque, the sense of this load torque changes with the direction of the motion of the drive. This passive load torque is existing mainly due to the friction feature and deformation in the non-elastic bodies. Consider the case of friction. The friction will be always in the direction of opposite to the motion of the body. That is, their sense of direction always changes with the direction of the motion of the body. So we can say that friction is a very good example for this passive load torque, because their sense of direction is always changing with respect to the direction of motion of the drive. So as a conclusive remark, we can say that the active torque is actually independent of the direction of the motion of the drive, whereas this passive torque is dependent on the direction of the motion of the drive. Or else we can also say it as in the case of the active load torque, the sense of direction of the that we are concluding today's session. In the next session, we will deal with the numerical problems associated with this fundamental torque equation and the concept of multi-quadrant operation and steady state stability. Thank you.